So now we get to the fourth part of the lecture. And the questions that you just went through, hopefully, deal with, well, what happens when you have wind that actually is accelerating. One case is here. When hurricane winds blow horizontally past the peaked or domed roof of a house, they tend to lift that roof upward and pull it off the house. This upward force develops because the airflow bends downwards towards the roof as it flows over the top of the roof. This downward bend towards the roof's upper surface indicates that the air pressure at the roof's upper surface is 1. Equal to normal atmospheric pressure, and that there is a strong unbalanced viscous drag force in the roof that's pushing the roof upward. 2. Lower than the normal atmospheric pressure, and that there is an unbalanced pressure force in the roof that is pushing the roof upwards. 3. Higher than normal atmospheric pressure, and there is an unbalanced pressure force in the roof that's pushing the roof upwards. Or 4. Equal to our normal atmospheric pressure, and there is a strong unbalanced pressure drag force on the roof that's pushing the roof upwards. Now, here's the picture that you would need. Is suppose that you had a house like so that has a roof, and you have a really heavy wind that's flowing over the roof. And again, the idea is that while it goes over the roof at this high rate of speed, there's a centripetal acceleration there, because there has to be. And so if you're well away from the roof, then what you've got is atmospheric pressure. But as you get closer and closer to the peak of the roof, then the wind has to go faster and faster. And so Bernoulli's equations would say that you have to have a low pressure here, that the pressure gets lower as you get closer to it. That way you get a net force in the wind, which causes it to go over the top of the house. Now, the problem that occurs is that inside the house, presumably it's atmospheric pressure. And so what you have is a low pressure air on top of the roof and atmospheric pressure inside the house, and that tends to naturally lift the roof off the house, which is why most of the failures that occur are because the roof pulls off the house. You can avoid that by basically reinforcing the roof so it's tied down to the body of the house, but that's about all that you can do. Now, the second question that you had is kind of related to it. It says, you live in a cylindrical high-rise apartment building. It looks like a giant upright can with windows. Your apartment has windows on the south side of the building, and you notice that the air pressure outside the window varies according to the direction of the wind. That pressure affects airflow into or out of your window. When the wind blows from west to east, the air pressure outside your window is above atmospheric pressure. Air flows out of your window. Above atmospheric pressure, air flows into your window. Below atmospheric pressure, and air flows out of your window. Below atmospheric pressure, and air flows into your window. So, here's the idea. Is imagine that you have a building that looks like this, and you're sort of sitting with the window on the south side. The wind comes from west to east. And so when it comes to the building, it's got to go around the building, like so. And so clearly, as wind goes around it, it's accelerating. In this case, the centripetal acceleration is towards the center once again. So if you're well away from the building, then you have atmospheric pressure. But again, as you get close to the building, next to your window, then you have low atmospheric pressure, so the pressure decreases. Inside the building, it's atmospheric pressure, and so if you have low pressure just outside the window, when you open the window, then air naturally just flows out of the window because it's atmospheric pressure inside the building, low pressure just outside your window. So the appropriate answer here is that it's below atmospheric pressure. That allows you to eliminate the first two, and air flows out of your window. And that's what you need. So the next one that we deal with is what causes the hissing in a faucet, hose, or nozzle. And the issue is one of turbulence, because essentially what we've always been dealing with is laminar flow, in which the viscosity dominates the flow's behavior, and so the nearby regions of the water always remain nearby. But This clearly is not what always happens. You also can get turbulent flow, in which the mass or the mass density of the water dominates the flow's behavior. And so there just isn't enough force to keep the water flowing together, and so nearby regions of water become separated. You can see this frequently. Let's see. Pretty sure it's down at the bottom here, these links. Let's go to this one. It's actually this one's what I wanted. And the idea is, if the flow is slow, then what you end up getting with laminar flow, this is showing dye running through a pipe filled with water. And if the flow of the water is slow, then what you get basically is just laminar flow. It gives a nice, even distribution. You can follow the dye all the way along the pipe as the water flows. But if you increase the velocity of the water just slightly, then what happens is that you start forming turbulence, and so you can start seeing that the dye tends to get separated as it goes through there. And this is a typical signature of turbulence. And it just matters about the flow speed. If the flow of the water is slow, you get laminar flow, and if you increase the velocity of the water, all else being the same, you start getting turbulent flow. And so the question is why? See how I'm doing on time. Okay. Now, this was well known, and it depends on what's called the Reynolds number. And the idea is the Reynolds number is basically the inertial influences over the viscous influences. And so if you have a large Reynolds number, then you get turbulence. A low Reynolds number gives you laminar flow. The inertial influences involve the density, basically the object length, and the flow speed, whereas in the denominator you've got viscosity. So generally speaking, higher flow speed, you get turbulence. Smaller viscosity, you get turbulence. So if the Reynolds number is below 2300, then viscosity wins, and so the flow is laminar. Above 2300, the inertia wins, and so the flow becomes turbulent. So you go laminar flow as you increase the Reynolds number by increasing the velocity, you get turbulence. This was actually observed first pretty early on by Leonardo da Vinci, who noticed that when water was flowing out of a sewer in the water, you could actually see turbulent flow. And it's seen lots of other cases as well. For example, around a baseball, higher rate of speed, you get turbulent flow. You can even see turbulent effects. You see these little vortices as you go around in the great red spot on Jupiter. So just one more series of questions, and then we'll finish up this lecture. We're almost done.